first of all, thanks everybody for coming. And this is the last talk, and I know you are hungry maybe. And I want to make the talk a little bit light and also very motivated. So this is a work about application of optimal transport theory, okay? In particular to quantum simulation. And this is joint work with we call Yunga's team, right? I think Marius is not here. I don't know. Maybe he's in a meeting. But okay, and also I include some ongoing discussion happening here and also inside our team. So first of all, I want to specify where I live, okay? Because I think it's really important in this seminar because people are from different spaces. We can clearly see that. So we have a Hilbert space, and we have finite dimensional Hilbert space. We have separable Hilbert space, and we have non-separable Hilbert space, right? And I guess for this one, most people, maybe more than half of the people here are living in the L2 space here, right? You are living inside this space because you are doing function theory. And if you're doing quantum theory, you stay in the right part, okay? And if you're pursue something like the most general case, you may stay in the white part, okay? And as I said, we are living in a Hilbert space doing algebra, okay? And what algebra are we doing? In the quantum case, we are doing this matrix algebra or a subalgebra of matrix algebra. And for PDE theory or for this stochastic process, you are doing L infinity as your algebra, right? Or a subspace of that. Not necessarily algebra, but you live in this L infinity algebra. And of course, I know there are some operator algebra people who always want to start from non-trivial phenomenon algebra because it includes both the quantum setting and the classical setting. Okay? And sometimes you have to assume trivial to make sure that most of the result can be translated to the most general to this general world, or the dragon called by David yesterday. Okay, let's talk about optimal transport theory, which is the main topic of this workshop, I guess. So the natural question is, what is the least cost needed to reshape one probability into another? Okay, and this picture is motivated from my experience earlier this year. I live in Canada, and this year there are a lot of snow, right? I have to shovel the snow from...
I can confirm that you were complaining a lot.
Yeah, sometimes I have to shovel the snow for 2 hours myself because...
In Waterloo?
In Waterloo, yes. It's really, really heavy, yeah. And I think about this, okay, how can I save my energy from doing this for 2 hours? Because whenever I do, the first time I did this, I can barely lift my arm after shoveling all the snows. Okay, so I think about, okay, is there a better way to transport the snow from this place to another place? This is the optimal transport theory. And in the non-commutative setting, which is part of our, which is the main theme of this workshop, we have to do quantum states instead of classical probability theory.
Quantum snow, not classical.
Yeah, quantum snow, yeah. You can just model the snow as a quantum states, of course. Yeah. And the main, I would say the most celebrated result is called the Monge-Kantorovich transportation cost. So this is defined usually, this is for finite dimensional setting, by the way. You find a subset of couplings of rho and sigma, and you choose a cost operator, and then you take the infimum over all the true cost, right? The true cost is given by the integral or the trace of the cost times the coupling. And another interesting formulation is the duality picture. So usually what you do is that you find a dual pair of your space. Okay? Usually the dual pair is motivated from the Fenchel transform. And you want to find a formula like this. And now let's talk a little bit about quantum simulation. Okay. So what is the motivation? So suppose you have an initial easy state, okay, initialized on a quantum computer, and you want to prepare some states, for example, some Bell pair, right, or GHZ states. What is the minimal number of unitary operator to transform one state, in the easy state, to another, okay, the target state? So if you see how to do that, what you do is that you find a quantum channel mapping from the initial state to the target state, and then you do the Stein spring dilation. I don't know whether you know this, but this is the result in 1950. Any CPT, completely positive trace preserving map has dilation. It's a unitary operator on a larger space. Okay? So on a quantum computer, we add a bunch of ancillas. That is the environment part of this Stein spring dilation, and you have a large unitary, okay, to model, to realize your quantum channel. And what you do is that you want to use a set of cheap unitary operators to simulate that unitary, okay, usually given by a sequence of unitaries or the product of the unitaries. So this gives you a very natural definition, which we call this count of U, which is the least number L, so that U can be represented in the product form. Okay? This is the most naive version of this problem. Okay? And sometimes in reality, you have something in a structured way. For example, on a quantum computer, it's not very hard to implement the unitary as a tensor product form. Okay? So you can implement one unitary as one unitary here. Okay, you can see in a vertical way. So you can implement such a unitary in an easily. Okay, of course it's harder than implementing one unitary, but you can usually do this in a combined way, so that you can save we can save the layers you need to use to approximate the unitary. Okay? So this is a special choice of your unitary operator. And in this case, we have a different notion we call the depths. Okay, this is the depths. So these two definitions. So first of all, depths is a special case of count, because you just choose your S to be all the unitary of this form. That is okay, right? But the depths plays a very crucial role, right? So in fact, it's a quite open question in quantum computing to find a particular state such that the depths of the unitary that prepare that state requires linear in n depths. Okay, this is a widely open question. People don't know how to do that. But for log n depths, people have a lot of characterization. Okay, so this is the theory. I think right now I want to see whether is there any questions. Okay, because I want to be a little bit slower than in this part, because I guess most people are not very familiar with this. Okay. If it is okay, I want to do a little bit summary of what is the current status or the current cutting edge knowledge about how to get lower bound. Okay. So the first column is about lower bound on the count. Lower bound on the number of unitary you need to approximate the unitary. You have three different tools, basically. The first one is kind of the trivial one. It's a commutator bound. So you only need to use the unitary invariance of the operator norm, and you use triangle inequality. Okay, this is a commutator bound. And the second one is more related to the coupling picture. So it's to find the geodesic distance from two states. And the third one is something called a counting argument. Okay, so it only works for special cases, but it's very sharp in some cases. The second column is about the lower bound on the depths. Okay, so the first is called the Schmidt rank. Okay, this is what computer scientists like. So Schmidt rank is that suppose you have a n-qubit pure states. Schmidt rank is the minimal number such that if you do Schmidt decomposition, how many product terms you need. Okay, this is the Schmidt rank. And the Schmidt rank gives you lower bound on the depth. Yeah, actually, the log of the Schmidt rank. So in the computer science community, they focus on how to get a Schmidt rank of pure states. Okay. And a kind of niche idea is Lieb-Robinson velocity. This is about time evolution of Hamiltonian, and we also have a discrete version. We call this light cone argument in computer science. Okay. And in this work, what we do is that we take the intuition from the first commutator bound and Lieb-Robinson velocity to get limitations of quantum simulation. Okay. But I'm not saying that these two are the best, but this is what we do. So the connection is that we show the minimal number of gates or the minimal number of depths for a quantum simulation task can be lower bounded by the transportation cost. Okay? So you have to choose your definition of transportation cost. And in particular, we choose the formalism given by Kohn and Riefel, right? So what is that? So we talk about the commutator. So the commutator gives you, the growth of the commutator gives you how your system evolve. Okay? And this is the original idea of Lieb and Robinson. And we define for arbitrary observable operator the Lipschitz norm of the observable given in this form. Okay? So there is actually a physical interpretation of this form. I think I don't want to go into that, but I will show you some proof, mathematical proof, why this can work in a minute. And in particular, from this semi-norm, we can define the Wasserstein distance using dual picture in this way. Okay, so you choose the dual pair as the diagonals of this Cartesian product, and you take this as your restriction. Okay, this is the distance. It's easy to check that this is actually a distance. And let's do some exercise. Okay, so the exercise is actually not hard, but is the core idea of our work. Okay, it's very simple, but you can easily see that in the more general setting, this one is essentially the key part. Okay, suppose you have U is given by you choose the minimizer, right? You choose the minimizing sequence U1 to UL that gives you U. And you use the so-called Leibniz rules for commutators, okay? And because everything here is a unitary, it doesn't change your operator norm. So you apply the Leibniz rule, and you get one-step triangle inequality. And you can throw away this unitary here. Every unitary can be get rid of. And you get this triangle inequality here, right? And then you iterate L times. You can get, this is upper bounded by L times the so-called Lipschitz norm. And here, this is also a Lipschitz form, right? This is a Lipschitz commutator, but you take the operator norm. So one remark is that it doesn't really need to choose the operator norm. You can choose some other unitary invariant norms. Yes. The second exercise is about the depths. Okay, it's slightly more complicated, but I want to say this. So this one is actually the idea of Lieb-Robinson. Okay, Lieb-Robinson bound. It's a discrete version. So the depth is defined as U. The depth of U is given by the minimization of all the product of V. V has this tensor product form. And each unitary here is actually local. Okay? And we can show that 2k to the depth is greater than or equal to this quantity. Okay? So let's go through the proof step by step. So first, you choose your S to be the one local Pauli operators. Okay? So don't forget. So P is one local. It only non-trivially acting on one qubit system. And the first step is given by the unitary invariance. And the second step here is using the locality property, right? Because P is one local, there is only one unitary acting non-trivially on it. So you can simplify your V. Okay? And the second step uses the commutator relation because UJP, UJ dagger is non-trivial on the K local system, right? It's only non-trivial on the K many subsystem. And you can freely add or subtract identity on the K local systems, okay? And after you do that, you move your UJ back, okay? By unitary invariance. Here, the inequality is something brute force. Like you have commutator, what you do is that you write it down and you do triangle inequality. Okay, so you have to pay a price of 2. And then by unitary invariance again, this P and UJ can be thrown away, right? So it's actually upper bounded by 2 times x minus this term. Okay, so if you are familiar with conditional expectation, it's a special case of conditional expectation, and this conditional expectation can be written as a Pauli channel, right? So it's a uniform weight Pauli channel, and this Pauli K means that it's the set of all the K local Pauli operators, and you have to make sure that it's uniformly weighted. Okay, and then by triangle inequality, you can get it's upper bounded by 2 times super of PK, right? And then you can, for PK, you use the Leibniz rule for commutator again. Yes. So you may think, okay, this is just a trivial task, right? But it's actually a little bit clever because if you do this directly from here, right? If you don't do the commutator trick, you do this the second line here. You just expand this operator in terms of K local Pauli strings. You have to pay a price of 2 to the K, not K. So this is an exponential improvement over K. So by doing this commutator trick. And finally, if you apply this V, V1 to VL, L times, each time you have to pay a price of 2K, so you have 2K to the L, okay? And then you get this term, and it's stated exactly the same as the exercise, okay? So after doing the exercise, we have 2 quantities, okay? So the 2 quantities is motivated from the exercise, which is given in this form, okay? So you have a channel. You can think of this phi as a unitary, and you take the unitary x acting on x minus x. This is exactly the commutator of your unitary as before here, right? I think I want to mention this part, right? So this unitary x commutator operator norm is exactly the unitary as a super operator acting on x minus x. Okay? So this is the how is it match. So you talk about these 2 quantities which play a crucial role to get lower bounds on the quantum simulation task. And this 2 quantity has some name. I mean, we don't really know how to call them. And for the first one, we call this transportation cost of channels. Okay, somebody calls this Wasserstein complexity, right? And here we can also call this Lipschitz cost. I mean, it really depends on who you talk to, right? If you talk to some computer scientists, if you call this complexity, this is really misleading sometimes because complexity is really about counting the numbers. But I think calling this as a cost is a more appropriate terminology, right? The second quantity is called the Lipschitz constant. It's plainly from the definition. And the connection here is that the first quantity is actually the maximum cost from any state, rho, to phi of rho. Okay? And the second quantity, as discussed by Roy on Monday, is actually equal to this Wasserstein distance contraction coefficient. Yes. So the second result, I would say, is not true in general, but only assuming that S is equal to S dagger. Then you can have that. Right? So this is the Wasserstein metric interpolation of the two quantities we introduced here. Okay? So I think I finished my background, or the motivation part of my talk, and I'm going to move on to some applications. Okay? Is that okay? So the first application is about limitations on simulation of Lindbladian dynamics. Okay? So this is a very old, we call this Church-Turing thesis. We want to simulate everything on quantum mechanics on a quantum computer. Okay? And we want to claim that it can be simulated efficiently using only unitary circuit model, okay, or the unitary operators. And recall that the Lindbladian generator in the most general form is given by this coherent part and the dissipated part. Okay, I believe that everybody is familiar with this, right? Because this is the topic which was very popular during the last few years. And the question is, given a set of accessible unitary operators, what is the minimal number of gates required to approximate this Lindbladian dynamics, e to the TL? So this is the question. We want to give some answers to this question in certain scenarios. Okay, and I want to talk about one example, which is how to prepare Gibbs states using Lindbladians. So suppose you have an n-qubit Hamiltonian, okay, and our goal is that we want to design a Lindbladian so that it converges to this Gibbs state. Okay? And the Gibbs state has this form, so it's e to the minus beta h. Beta is interpreted as the inverse temperature. So it's a very simple idea, okay? People knew this idea for more than 2 decades, I believe. But there's still something to be discovered in this, in this business, I would say this. So we want to design a Lindbladian, and also we want to efficiently simulate this Lindbladian. Okay? So the designing of this Lindbladian is kind of tricky, and which I will show you now. So what are the two candidates for this type of Lindbladian? So you want to have some symmetry, right? You want to modify, you want to emulate it. Okay, you want to emulate the classical setting. So classical, you always want to have a sigma detail balance condition so that it can converge to that target state and converge fast. And in the quantum setting, there are two very different classes. Okay, so the first is the so-called GNS symmetry, right? So you have to preserve this kind of symmetry. It's eventually this. If you see this rho beta as the state, okay, so it's under the state, it is symmetric. So the second one is you do this. We call this non-commutative. So this non-commutative. We call this gamma rho, right? It has a name. I remember there's a name for this by Afros, which was a professor here. So they call this. This is a very crucial non-commutative quantity, right? This is very
polar form. Agro baptized the self-polar form.
Okay, polar form. Yes. So in fact, these two symmetries are very, very different in reality. Okay. So let's talk about the issue for this GNS Gibbs sampler. So GNS is the first one. Also, by the way, I want to have a remark that GNS symmetry is much stronger than KMS symmetry. So it's a smaller class. You put a very strong symmetry on your system that it cannot happen in physics. Okay, so that's the point.
Please remind us the abbreviations.
The derivations?
Abbreviation KMS stands for Kubo, Martin.
Oh, yeah, KMS. Kubo, Martin and Schwinger. Yes.
And what?
I forgot the name. Sorry for it. I'm bad at
Schwinger, yes. And the second one is Gelfand?
Oh, the Gelfand Nijmegen.
Yes, yeah, it's good to refresh memories.
Uh-huh.
So, Gruber, Martin Schwinger, and Gelfand, Neumark.
Nijmegen.
Okay.
Okay.
So let's repeat it too many times, you will memorize.
Yes, I only remember the initials, but yes, that's and thanks for pointing that. Okay, it's good to remember the names. Yes. By the way, in the paper by Eric and Yan Mas, they have a very clear explanation why GNS is a stronger symmetry assumption on the Lindbladian dynamics. So essentially, GNS detail balance is equivalent to saying that the Lindbladian generator commutes with the modular automorphism group. Okay. So the modular automorphism group is given by a T. Okay. You have rho to the IT left and rho to the minus IT on the right. And a trivial application of this commuting property is that the jump operators must be the eigenvectors, eigenoperators of the modular automorphism group. Okay, so modular automorphism group is actually a supermap, right? It's acting on operators. So you have to talk about eigenoperators. Okay, so this is the reason why I choose this word. So physically, if you have this strong symmetry assumption, the dissipative part, or the jump part, must know about the entire spectrum of the Hamiltonian. Okay? So this is a physical meaning. Because you have this, you evolve with T, right? So after you apply this modular automorphism group, you have a phase shift. Okay? And for all T, and you have to know exactly what is the eigenvalue of the Hamiltonian, or e to the minus beta h. And this is a physical argument. By energy-time uncertainty principle, it requires exponential time to implement such a GNS Gibbs sampler. Let me explain, okay? So energy-time uncertainty principle means that the energy difference times the time is a constant, okay? And the energy difference is very, very small in this case, because you have, suppose your Hamiltonian is an n-qubit local Hamiltonian, right? So the largest energy is linear in n. So, but you have 2 to the n many energy levels. So the energy gap must be very, very small. So the time you need to prepare to implement such a Gibbs sampler, it requires exponential in time. This is a folklore. I mean, I talked to some experts before February this year. I didn't know this, but this is a folklore in the experts inside a community of experts doing this business. They said that okay, for GNS, for non-commuting Hamiltonian, you always have this trouble. There's no mathematical proof for this. Okay, I think using our framework, we cannot really show that because this is an exponential in time lower bound. And but by this energy time uncertainty principle, of course, it's a plausible proof. I mean, it's a physical proof, but if you don't buy it, it's okay, right? As a mathematician, but this is what they believe. And let's talk about why KMS Gibbs sampler is actually a remedy for this business. Okay, so you have to use KMS. You cannot use GNS. I want to recall a well-known result. I don't know whether it's well-known in this community. So a Lindbladian generator satisfies KMS symmetry if and only if L can be written in this form, and it satisfies these 2 extra assumptions. So if you're familiar with Cartan mass setting, so which is GNS setting, your V and V dagger are commuting, I mean, with this, we call this modular operator. But here you have this weaker notion. Okay? So this weaker notion in physics actually allow you to not knowing the whole spectrum of the Hamiltonian. So it can save you some time in this Lindbladian generator.
Sorry, can you remind us, is LVK only the jumps or the full dissipated part?
Lj is given by, LV is defined as Vx V dagger minus 1/2 V dagger V X. This is anti-commutator. Okay, this is your V. So the jump operator does not really comes in pairs. Like coming in pairs means that the set of Vj is equal to the set of Vg dagger, right? This is the sigma detail balance. But here we have a weaker notion here. And G is something, it's a remedy for this KMS. So suppose you have your jumps, you must have a Hamiltonian part to make sure it's pulled back to a KMS symmetry. Okay, so this is the the characterization of KMS. I don't know whether it's well known, but it's a simplified version of the result by Fagnola in 2007. Okay, you have, this is just try to match the characterization by Carlin mass paper.
Well, it's in my paper with Eric Amarin. He did the parameterization of KMS generators.
Oh, okay. Thanks. Yes, it's actually in Eric's paper, I think, right? Yeah. So if you have that, how do you design your KMS Gibbs sampler? Okay. So the KMS Gibbs sampler is given by the interaction picture and by a weight, and the weight is actually dependent on the temperature you have. Okay. So this is your standard choice of the jump operator, and the question is how do you choose your function f? So once you choose your function f, which is usually Gaussian type, and you can use the KMS characterization to add your G part, right? To make sure it is KMS symmetry. And this one ensures that your Lindbladian dynamics has a unique fixed point, okay? So this KMS Gibbs sampler is easier to implement, okay? So you only need to use the Hamiltonian evolution, and we call this energy gap filters. So what is that? That is actually the sigma J's, right? So it's very, very simple. It's something like, it's a local Pauli operators, and on both the original system and on the environment system. So you only need to use these two accessible unitary operators to approximately simulate your Lindbladians. Okay, so this is a KMS. And I want to talk about the limitations of this. First of all, this is an efficient Gibbs sampler because you only need polynomial in n many circuits to implement this. And now in this case, we can show a lower bound. Okay, show a lower bound. And our result is this. So using only the Hamiltonian simulation and the energy gap filters, if the temperature is really, really high, okay, high temperature means that beta is very, very small. Okay, I have a remark. The beta is very small. If beta is 0, your Lindbladian dynamics is actually a depolarizing channel. Okay, depolarizing channel. If you know that, right? But beta is very small. It's very close to a depolarizing channel. In this case, we can show that the lower bound must be limited by this energy gap, largest energy gap of the Hamiltonian. Usually, the right-hand term is linear in n, or polynomial in n. And because we assume that high temperature, we can even relax the time from a small time to a small constant time, by this rapid mixing property for this Lindbladian. And the remark is that our method here is actually restrictive to rapid mixing dynamics if you want to get constant time lower bound. And in the last workshop, Kiani's talk, right? He talked about the slow mixing of this Gibbs sampler. He showed that when the temperature is very, very low, right, and it's actually the mixing time is very, very small. The mixing time is very large, so that mixing is very slow. It's exponential in n, actually. And for this type of Lindbladian dynamics, I think what is quite wide open is that whether modified log-Sobolev inequality is true in this setting, right? I don't know whether Marius agrees because he thinks he has an example, but my claim is that find a GNS and KMS symmetric Lindbladian, which is a non-commuting, which admits the Gibbs state of a non-commuting Hamiltonian as a fixed state, and MLSI should fail. Okay, so this is nobody proved this, but this is a very interesting question. And in this case, last time Daniel talked about the proof how we can get rapid mixing. The approach is that they show the Lipschitz constant of this Lindbladian decays exponentially. And here the lambda should be dimension independent. And then you can get rapid mixing. Another remark I want to have is that this condition, so the Lipschitz decaying condition, is equivalent to log Sobolev inequality in classical global dynamics. Okay. In the quantum setting, these two are probably not equivalent. Okay. So you have to use this Lipschitz approach to get mixing time rather than going through these functional inequalities. Okay. And sometimes, and some other people call this, this is called the coarse Ricci curvature, or the discrete version of the curvature of the system. Okay. And it shows that this method can work well. Yeah.
So, so a stupid question. What is MLSI? What fails?
MLSI means that the so suppose you have your relative entropy, right?
No, but what means those letters?
For lattice. No, I mean this definition holds for arbitrary Lindbladians.
Modified log Sobolev.
Ah, okay. Modified log Sobolev inequality.
Yes.
Thanks. No, it's enough. It's enough.
Oh, okay. So you know that.
Yeah, but it's good to know what are the abbreviations.
So this means that the relative entropy of the state over time, given the Gibbs state, is bounded by e to the minus ct d of rho given rho.
Sorry. It's even written here, but I have not associated. MLSI is good to. You use this name, but sorry.
Yes.
It's good to put it immediately in the brackets.
You should maybe say that not every TT you can write down will automatically satisfy the Daniels estimate. They work very, very hard to get it, right?
You can always get it, but the lambda is dimension dependent.
Good estimates for this lambda are still hard work.
It's really hard. Yeah, I agree. But in general, if TT is it's converging to the Gibbs state, and this one will always converges to zero. Okay, right? Converges to zero. So because the Lipschitz constant of the so-called replacer channel is always zero, so it must decay to zero. But what it matters is that how to choose this lambda dimension independently. Okay, and the proof I would say is something like it's a bunch of cluster analysis for this n-qubit system, and I will not talk about that. But I want to say that we use this condition here to get a constant time lower bound. This is the crucial part, and this is the reason why we assume that the temperature is very high. Apart from that, it's wide open. I think I finished the first application. I only have 10 minutes, right? Or 6 minutes, is it? 10 minutes, okay. And I want to talk about how to get lower bound on the depths of a quantum channel, okay? Remember, we introduced two quantities, okay? This first quantity, we applied it to Lindbladians, and the second quantity, we talk about the depths of quantum channels. And our general principle is that if you have your channel given by a product, or we call this a layers of channels, then we choose any resource set S. L is lower bounded by the log of Lipschitz constant of phi divided by log of Lipschitz constant of the component, right, of the subparts. If you remember, this term is log of 2k. And this term, we just want to see whether it scales with n or exponentially uneven, but we don't know that whether this one can give you linearly n lower bound. Yes. So I think I forgot to add here, if you can get L is lower bound, an explicit example of phi, so that L is lower bounded by n, I think it's a quite open question, yes, in general. I want to talk about a concrete lower bound on using the Lipschitz constant. Okay, and this idea is already in the computer science literature, but we can give this Lipschitz constant reproof and do a little bit better. So the setup is that suppose we have an orthonormal basis for the n-qubit system, and we have your initial state and you have an output state. And we define the measurement probability of your output states by doing measurements on this orthonormal basis. And in the computer science literature, they always choose this orthonormal basis as the computational basis, which is all the bit stream basis. But here, we don't need to assume that. So the main result is that if we have a circuit, meaning U is a unitary operator, we can get a lower bound of the Lipschitz constant. So the first constant is depending on the choice of the set A. Set A and B are the subsets of the bit string, okay? Subset of bit string. And F is an arbitrary function. Okay? So it's minimized over all the function, the difference of function acting on A, function acting on B. Okay? And you have to pay a price of this Lipschitz constant here. In reality, what we usually choose is that you choose A and B. Okay? You choose your function F as the distance function to A or to B. And this will recover the Haro-Alder. So sorry, I think it's not LIDAR, it's Haro-Alder argument. And they call this well-spread property for the output state. Okay, sorry. So this is the classical literature. They already have that, but we have this flexibility of choosing A and B and F. And in classical settings, the hard part for them is that they can always do commuting Hamiltonian. And using this approach, we expect to have some non-commuting Hamiltonian lower bounds. That can, hopefully, that can be interesting to that community, but I'm not so sure. Yeah. I think my talk, I just want to finish the talk now, because the remaining part, I believe that one of our collaborators will come here in June and talk about the details following this direction. Yeah, it's in June 8th. It's a reunion workshop, right? So that's, I don't know whether you know that. So usually we have a workshop. After 1 year or two, we reunion to recover or to discuss what we did 1 year or 2 years ago. Yes. So in 2023, there's a similar long program in IPAM, and they're going to reunion in June. Yes. So one of the collaborators will talk about this. Yeah. So that's the reason why I want to stop here. And thank you for your attention.